So here's some spectra of some various halogens. We've been talking a lot about the halogens, so I thought this was a pretty cool spectra to show you. The first thing I'll show you right away here is look at the Y scale. Okay, so you're used to seeing an absorption spectrum as A versus lambda, right? Absorbance, where you get, some kind of peak, right? Owing to where the molecule absorbs that radiation. However, if you express a spectrum in terms of its cross section, right? There it is, centimeters squared per molecule. And look, it's telling us base E. Fantastic. Then you have an absorption spectra where you don't have to specify the concentration, nor do you have to specify the path length. It is a general, fundamental way of looking at a spectra. Concentration, path length, not required. The other thing that I want to show you is oftentimes, so if we write 10, 20 sigma like that, like it is done here on the scale, that means the cross section has been scaled up by a factor of 10 to the 20, okay? So in fact, what that means is this number right here, this 3.1, that's really 3.1 times 10 to the minus 20 centimeters squared per molecule. So cross sections are supposed to be very small numbers, which makes sense because if you think about this as a cross section, right, like as some cross sectional area, right, where light passes through. So if let's say I've got a bunch of waves passing through, this is really what this cross section is giving us, okay? So then perhaps these beams of light were being absorbed by that cross section. So now only those beams right there will make it through, okay? So it does represent like some cross-sectional area that's a target for photons. So it's supposed to be a small number. So just keep that in mind. When you see the exponent in front, 1020 sigma, what it really means is sigma times 10 to the minus 20. I know that's a little backwards, but that's common in the literature, okay? So now what I want to point out, I'm going to highlight a few things. Let's start with purple. So this number 1 here, oops, I wanted purple because as you can see, it's in the ultraviolet region. So I'll highlight this spectra right here. Here we go. Spectra number 1 right there is F2, all right? And you can see it's got a lambda max, something like around 275 nanometers or so, all right? So if I was doing photochemistry with fluorine, I would want to select a light source that's somewhere between these wavelengths for fluorine, right? We can see fluorine absorbs between 200 and all the way to 400. So if I picked a light source to do photochemistry on fluorine way out at like 600 nanometers, nothing's going to happen. The fluorine doesn't absorb 600 nanometer light. What I would really want to do is choose a light source that's very close to the lambda max, right? That would give me the fastest possible photolysis rate constant, okay? So the next one, let's see, I'll go with maybe like a blue color. Okay, so the next one, as you might guess, in order of the periodic table is going to be chlorine. Right there it is, number 2, chlorine gas. Okay, very cool. And you can see its lambda max shifts to a slightly longer wavelength, which makes good sense when you consider the ionization energy and the other periodic trends of these halogens. All right. And then now let's see here. You can see number 3, hopefully you might guess, is gonna be bromine. Let's pick a nice orange color for bromine. All right, so bromine's got that interesting little shoulder right there. So lambda max for bromine is around 400 nanometers or so. And then finally, let's use red. Iodine, Igor. Okay, so scales as well. And what's kind of cool about this, if you read through this, right, so fluorine is a gas at 25C. Chlorine is a gas at also 25C, but for some reason the spectra is at 18C. Bromine is a gas at 25C. However, iodine is not a gas at 25C. So that's why this iodine, number 4 and 5, there's some subtle differences. Number 5, the one I highlighted, is actually iodine gas plus 1 atm of bath gas, of atmosphere. Whereas this number 4 is just pure iodine. And so there's some interesting things going on there. We'll get into those details when we get into spectroscopy. So, but I mostly wanted you to be aware of this trend for the series of halogens, but also just as an example of if I was doing photochemistry on the halogens, I really want to select a light source that's appropriate for a given halogen, okay? Or whatever molecule I'm interested in, all right?